Assalamu alaikum. In this video, we'll see how we can find the probability for a range of random variable values when it is following normal distribution. The probability is calculated for the range of random variable values when it is following in a continuous distribution. And normal distribution is one example of continuous distributions. For continuous probability distributions, the probability of any single specific value of random variable is infinitesimally small, very small, which is very close to, or practically we can say that it is equal to zero. So you will see this in most of the places mentioned for a continuous random variable, the probability of the random variable assuming one particular value being practically equal to zero. So for this reason, we always find the probabilities of random variables following continuous distributions in as a range or an interval of values for the random variable, such as you will see this kind of probability calculations. Z is less than -1. Again, equal to at exact that point, it is going to be practically equal to zero. So P is less than equal to -1 or P is less than -1 is practically the same. Now, here you see Z. We have discussed this already, that the normal distribution, in order to avoid computing that complex mathematical function which defines the probability density function for the normal distribution, we have already computed values in standard normal tables, which we are going to be looking at today in this video also. And for this, we need to convert our random variable into standard normal. And we compute the z-scores for all the values of the random variable of the original population, which might be having any value of mean or any value of standard deviation. But we transform them into standard normal distribution, which has 0 mean and 1 standard deviation. And these are known as the z-scores. And we already know the expression to calculate z-scores. So here you see probability of z is less than -1 is basically the cumulative area under the curve towards the left of this point on the x-axis. So here you see the shaded area. This is basically the area that we need to calculate under this curve. And there are mathematical functions available for that. But since this has already been done and consolidated in form of tables, what we need to do is only go to the tables and find the value that we're looking for. In this case, we're looking for a value of z, which is -1. And whatever we find from the table is this area towards the left of it. You need to keep this in mind, that whatever value you look up from the table is the area to the left of the point of the reference point. Here, the reference point is -1. So at whatever value of probability you find from the table is basically the probability of a value being less than -1. It is the area to the left of this point. Of course, this is quite a big area towards the right of it also, but the tables specify the area which is to the left of this point. So you get the probability of values being smaller than this value that you're looking up from the table. The cumulative areas are pre-calculated in the standard normal tables for quick lookup. So this is how a standard normal table looks like. This is standard normal distribution. Table values represent area to the left of the z-score. And again, the left is highlighted, written in bold and big letters, so that you remember that whatever probability value you read from here is basically the probability area towards the left of this z-score that you are looking up. And it is the probability of values being smaller than this value. Now you can see that this is column which lists all the possible values of z, specifically the first two digits of the z value, which has 1 before the point and 1 digit after the point. And then you have these values starting from 0.0000 to 0.01 and all up to 0.09, after which, of course, this second decimal place will become 0, and you will have a new value of the next value of the first decimal place. So the value on the left of the decimal and 1 digit on the right of the decimal, you have to look those values up from this column first, and then we go for values for the second digit after the decimal. So for example, if the value that we're looking up is -3.28, we are going to find -3.2 from this column. Here we can find it, -3.2. And now we need to look up for 0.08, because the value that we are looking up altogether is minus 3.28. So from here, we find the column which corresponds with 0.08. And wherever these values intersect, which is this one, this gives us the probability of z-score being less than minus 2.8, 2 point, which value actually, minus 3.28. So this is the probability value, which is 0.00052. This is how you will look up the values. So we have all the listing of the negative values that the score can have, and all the listing of the positive values here. And you see that you do not have a listing of values beyond 3.9, because we've seen that most of the 99.7% of the values will lie between the first 3 standard deviation. So you will see very little probability of values, because these are the values towards the left. So you see why you see very high probability values here is that because these are points on the right half of the curve, and the area is being given for the left half. So it covers almost the entire area. So this is almost equal to 1. But if you look at these values for the negative values of z, the area is towards the left, and which means that we're scanning from left to right. Of course, the area that it covers is on the left, so it starts from being very small, and then it goes up to being bigger, and then finally when it covers all the values. So you will see very small probability values for values of z greater than 3 in magnitude, be it minus or plus. The probability values are going to be very small. From here, you should also notice that whatever value we are getting of probability from this table is always for a range which is smaller than the value we're considering. So if it is, you look up for something from here, say 1.82, it will be, we find 1.8 here, and for 0.2, it's this one. So we have 0.96526. Why is it so high? Because 1.8, we are looking for the probability. This probability value is actually the probability of z being smaller than 1.82. And this table does not tell us the values of z being greater than 1.82. So we will have to do one little extra calculation to find that out. And it is very easy. It can be done using the laws of probability that we have already seen. So if you're to find the area under the curve, or the probability value corresponding to z is equal to 2.71, now we only need to look this value up in the standard normal tables. And this is basically equivalent to asking, what is the probability of observing a z value less than 2.75? So we just need to find out the row which corresponds to 2.71 z value. And then from the columns, we'll select 0.01 because the value is 2.71. And we find that the probability value against this z-score is 0.9966. Now you see that this is a very high value. And this can be demonstrated with the help of this graphic. Here you see that 2.71 is a value quite farther away from the mean, towards the right side, towards the positive side. And we have already discussed that it will be the probability of observing a value of z value greater than 3 is going to be very low. So most of the probability is also the area under the curve is already quite almost completely covered by values very close to c, towards the right, away from the mean. So this is the reason that we see that the value which corresponds, probability values which correspond to z-scores greater than 2, the probability values are very high in this case. Let's see this with the help of an example. The amount of time students of semester 1 take to complete their lab tasks is a random variable following the normal distribution with mean equal to 1.75 hours and standard deviation being 0.6 hours. What is the probability that a randomly picked student takes less than 1.5 hours to complete her task? Now we've been told that this random variable, which represents the time taken by a student to complete their lab task, is following the normal distribution. And for normal distribution, we know that in order to completely characterize a normal distribution, we need to know 2 values, which is the mean and the standard deviation. And we have been provided those in the data, in the description of the problem. Here, we can write that X is following a normal distribution with mean 1.75 and 0.6 as the standard deviation. And we are to work out the probability of x values less than 1.5. And now we need to convert this value, the x value, into z-score, so that we may be able to look the value up directly from the table, and we do not have to do the complex computation of the function of the PDF of a normal distribution. So here we convert the x value into corresponding z-score. For 1.5, we use the same expression. The z-score expression, you're going to see that very frequently from in the coming lessons also, because it will be used in many of the calculations that we will be doing in the coming lessons. So here we have x, which is 1.5, minus mu, which is 1.75, divided by sigma, which is the standard deviation. X minus mu over sigma is the expression which converts an x value into its corresponding z-score. Here we get minus 0.42. And why we have a minus is because we are looking, we're working with a value which is less than the mean. So it is towards the left of the mean. Mean of the standard normal distribution is 0. Any value which is to the left of it is negative. Here, it's always a good idea to plot the curve, to draw the curve, so that this avoids a lot of mistakes. And it's better that you mark the point and share the area that you are actually working the probability for. So here we get minus 4.2. We know that it is to the left of the mean. So the point is somewhere here. It is, of course, to the right of -1 and between 0 and -1. So we have the point here. And this is the area that we're working for. How do we know that we're looking for the area to the left of this point? Is because we're working for a probability value for values which are less than a given point. So this is the left area. And this we can look directly up from the standard normal table. So by looking up from the table, we get this value, which is 0.33724. So there is a 33.72% chance that a randomly picked student will take less than 1.5 hours to complete their task, which is almost 1/3 percent, one third chance that. Okay, so now there can be 3 cases to find probabilities with normal distribution. One that we have already seen, which is if you need to find out the probability for x values being lesser than a given reference value, this, in which case we look the values directly up from the table, because these are the values which correspond to the area to the left of the point which is given, and these probabilities have already been worked out and given in the tables. The second is when we are to find the probability of values occurring above a given value of x, in which case the expression would be p of x is greater than x. Now, these values are not directly available in the table, but we can make use of the loss of probability to find these values. And in this case, actually, these probabilities are corresponding to the area to the right of this point that you are looking for. And again, I keep on repeating this. The values given in the standard normal table are areas to the left of the given points. Here, in case of the probabilities for values higher than a given value, we are looking for the area to the right of this point, which is not directly available in the table. But of course, we can do an extra step of calculation to find this probability. The third case is when you are finding probabilities of values occurring between 2 points, x1 and x2. In this case, the expression is this, as written here, p of x being greater than x1 and less than x2. Now, this is the area under the curve, which is between 2 points. Of course, this value is not directly readily available from the table, and we need to do one extra step of calculation to find these values. And we'll see how we can do that. So to find the probabilities for values of x greater than a given value, find the area under the curve to the right of this point, which of course is not available in the table readily. So P of x is greater than x is cumulative area to the right of x. And this is depicted in this graphic. Here you see that this is the z value that we're looking at. Area to the left is what is given in the tables. And this is the area to the right, because we want to know the probability of values which occur, which are greater than this value z0. So in this case, what do? The standard normal tables provide cumulative areas to the left of the given points. So the area to the right of it is found by subtracting it from the total area. We know that the total area under this curve is 1. So by the law of complement also, if you are to look for values which are greater than x, we find the probability for x values lesser than a given value x, and then we subtract it from the total probability, which is 1, and we get the value of the probabilities for x values occurring above a given reference point. So this is how you do it. 1 minus p of x is less than equal to x. And p of x is less than equal to x, you find it directly from the standard normal tables. Let's do this with the help of an example. The time to implement a medium-sized course project by semester 5 students is normally distributed random variable with mean 11 hours and standard deviation 3 hours. What is the probability that a randomly selected student would take more than 15 hours to complete their project? And now clearly you can see that we need to find out the probability of x occurring above a given threshold. And for that, we know x is the time to complete the project, and it is following a normal distribution because it is stated in the question data. We have x following normal distribution with mean 11 and standard deviation 3. Now, p of x is greater than 15 is what we need to find out. So we find the z-score corresponding to 15, and we get it as 1.33. Again, it is a good idea to draw the plot so that you do not make any errors and shade the area that you are interested in. So here, since we need to find the probability for something greater than a given point, the sign is greater than, the area is to the right of that point. The point is 1.33, which we plot here. It is between 1 and 2, of course, farther away from the mean on the right side. And to find the areas to the right, we always subtract it from the whole, because the only thing that we can get from the tables is the area to the left of this point. So when you will look up for the value 1.33, you get a probability value. This probability value corresponds with the values of z being smaller than 1.33. And that is why we subtracted from 1 to get the probability values for the value of z being greater than 1.33. And this is what we get. From the lookup table, we get the probability of z is less than 1.33 as 0.9028, and we subtracted it from 1 to get the desired probability, which is the probability of z being 1.33 greater than 1.33, and actually to find the probability of x being greater than 15 hours. So this is the probability. 9.18% chance that a randomly picked student would take more than 15 hours to complete their project. Now to the third case, when the probability values are to be found for probability of values occurring between two endpoints, or an interval of range is to be found out. Interval with 2 endpoints specified. Here we have, if we are to work out the probability for x being greater than equal to x1 and less than equal to x2, again, please ignore being equal to or not here, because we have already discussed that is, even if you miss out the equal to sign, it's not going to make any much of a difference, because we've already discussed that with continuous random variables, the probability of observing one specific value at one given point is practically equal to 0. So it is it's the same if you write it as x is greater than x1, or if you write it as x is greater than equal to x1. Okay, for the case when we have two intervals specified by 2 endpoints, this is how we compute the probability. And the reason for this is we do not have the probabilities specified in the any table which we can read directly to find this probability. Now this can be more explained more clearly with the help of this image. And you see here, this is point x2. Which is, of course, a higher value than x1. So it is the higher endpoint. Now you see, when we look it up in the probability table, it is going to give us some value which corresponds to this entire area from the start up till this point x2. Now, when we look up a value for the probability value against x1, we get the value of the area under the curve from the start till this point x1. So what we get for x1, x2 already covers what we get for x1. In order to get the values in between, or this area which is lightly shaded here, we can subtract this area which we get for x1 from this whole area that we get from x2, get for x2. So the area that we get for x2, which is p of x is less than equal to x2, which we looked up from the table, we subtract the area that we get for x1, which is p of x is less than x1, which again we look from the table. When we do this subtraction, we get this area, which is lightly shaded here. And this is the probability of having a x value between x1 and x2. And of course, these values we can look up directly from the table. And we use these to find the area between them. An example is the same example, and now we are to work out the probability of what is the probability that a randomly selected student would take more than 9 hours, but fewer than 12 hours to complete her project. Okay, so X is the time taken to complete this project, and we've been told that X follows the normal distribution with 11 as the mean and 3 as the standard deviation. And this is what we need to find out, which is X is greater than 9 and less than 12. So we find the z-scores. But now in this case, we have two endpoints. We need to work out two z-scores for both of these points, for each of these points. So for 12, we get it as 0.33. And for, of course, because 12 is greater than mean, so we expect a positive z-score. And for 9, we get minus 0.67. Again, because 9 is smaller than the mean value, which is 11. So we know that we're going to get a negative z-score. Now, we need to find the probability value for the higher z-score and subtract the probability value for the lower z-score to get the probability value for values between these two endpoints, between 9 and 12. So this is P of z being greater than equal to minus 0.67 and less than 0.33 is equal to P of z is less than 0.33. Why do we have a less than here again? Because the probability table is only going to give you values for the less than intervals, not for the greater than intervals. So we find the value for the higher z-score and we find the value for the lower z-score. And we subtract the value of the lower z-score probability from that of the higher z-score probability. And then we get this shaded area. Again, it is important that you draw the plot and mark the points and shade the area that you are looking for. So here, we get the probability for against 0.3 against the z-score 0.33 as 0.6293 and for minus 0.67 as 0.2514, and the probability of observing a z value between these two values is 0.3779, which means there is a 37.79% chance that is randomly picked student would have taken more than 9 hours, but less than 12 hours to complete her project.